Welcome back, everyone. This is the last section of this test 3, and I promise it won't take a super long time, but I wanted to go over, sort of in one place, these words I keep using about vertical and horizontal asymptotes. So here's a typical graph of some sort of rational function. And in this graph, there are a few different things going on. Namely, there are these 3 dashed lines. And the 3 dashed lines are there because the arrowed pieces of the graph are getting closer to one of the dashed lines. In this case, these 2 dashed lines are vertical, and in this case, that dashed line is horizontal. These dashed lines are all called asymptotes, and we call the vertical ones vertical asymptotes and the horizontal ones horizontal asymptotes, as you might guess. Okay. I want to make sure we're comfortable writing down the equations of these. So in this particular instance, the equations of the vertical asymptotes are given by this 4 and this minus 2. But note they're vertical lines. And so what that means is their equations look like x equals, and in this case it's x equals 4 and x equals minus 2. Those are the equations of my vertical asymptotes. Again, vertical lines always have equations that look like x equals blah. And so, in this case, those happen to be x equals 4 and x equals minus 2. The horizontal asymptote, on the other hand, in this case is this horizontal line. And horizontal lines all have the flavor y equals blah. And so in this case, this horizontal asymptote happens to be y equals 3. So these are the 3 asymptotes as we would describe them. This is their equations. Now, in terms of limits, where did these come from? Okay, so let's do the horizontal asymptote first. The horizontal asymptote here is coming from the fact that as I take really, really, really large inputs, the output is very close to 3. So namely, this y equals 3, it comes from the fact that the limit as x goes to infinity of this function is 3. Really large inputs give me outputs very close to 3. And actually, the left-hand side also gets closer to 3. And so, in fact, the limit as x goes to minus infinity of our function f of x, it's also 3. Really huge negative inputs also give outputs very close to 3. Okay. So this is how you talk about horizontal asymptotes in terms of limits. They are the limits at infinity and minus infinity. I'll note, if we look at something like this, where the limit as x goes to infinity is plus infinity, we do not say that the function has a horizontal asymptote at plus infinity. Okay. In this instance, if you look at both directions, both of these are infinite. One's positive infinity, one's negative infinity. So we just, in this case, say no horizontal asymptote. We wouldn't try and force it and say y equals infinity or y equals minus infinity. Okay, what about the vertical asymptotes? Well, the vertical asymptotes here at minus 2 and 4, they come from the fact that, for example, if you take the limit as x goes to 4 from the right of this function, then you get something infinite. Okay. Namely, instead of this being 2 or 7 or something, you get a negative infinity. The graph inside at the input 4 spikes off to minus infinity in one direction. That's what tells me that this is a vertical asymptote. We talked about this kind of limit in the last section, 2.4, and we learned where this came from. Namely, this came from spots where the denominator was 0, but the numerator wasn't. So vertical asymptotes come from zeros of the denominator of a rational function that are not also zeros of the numerator. Okay, so let me give you a quick rundown of all the combinations of the numerator and denominator being 0. So if neither are 0, what does that end up looking like in the graph? That ends up looking like basically nothing. It's just a point. If the numerator is 0, but not the denominator, what does that end up looking like? Well, there, the function is just 0. So this looks like an x-intercept. Okay, what about not the numerator, but the denominator is 0? What does that end up looking like? That's the description of vertical asymptotes. And so this is where we end up with something that looks broadly like this. And what about both being 0? This is where we end up getting a hole. So here we have some perfectly normal function minding its own business, but then we come across this spot where the function just randomly is undefined. And so this is the 4 combinations that we keep seeing. And so I just want to emphasize this because it's easy to get these confused. So this is the first one we talked about. All the way back in section 1.2, we were figuring out where fractions were equal to 0 by setting their numerators equal to 0. In section 2.2, we calculated a giant pile of limits that all amounted to factoring something out of the numerator and denominator and canceling it. Those were all the 0 over 0 style limits. Those all amounted to this kind of thing. Then, in section 2.4, we started talking about these spikes and deciding when these spikes went up or down. And so we can label each of these. So this was in section 1.2, this was in section 2.2, this was in section 2.4. Okay, to wrap this section up, I want to take these 2 different functions, and I want to find all the things we know how to find. So we know how to find x-intercepts, y-intercepts, vertical asymptotes, and horizontal asymptotes. And I want to try and find all of those things and make sure we understand from those what the graphs of these functions have to look like. Okay, so let's start with the y-intercept, because that one's always the easiest. So it's 0, comma, and then what you get when you plug in 0 for x, because the 0 here is an input. So you would get minus 2. Okay, over here, when I plug in 0, I get plus 1/4. Okay, how about the x-intercepts? Well, I get x-intercepts by setting the numerator equal to 0. So 2x minus 4 is equal to 0. That's going to give me x is 2. So that's going to be my x-intercept for this one. In this case, I set the numerator equal to 0, and then I get x equals 1. So that is my x-intercept. Okay, let's next look at horizontal asymptotes. So this is going to come from the limit as x goes to infinity of 2x minus 4 over x plus 2. Okay. Remember to calculate this, the thing I do is I throw away all the lower order terms. So that is, I write the limit as x goes to infinity of just now 2x over x, because x to the first is the highest power of x in both of these, which is the limit as x goes to infinity of 2, because I can cancel the x's, which is just 2. That says that this function has a horizontal asymptote at 2. Okay. Take a second. Is this an x equals 2 or a y equals 2? Squint your eyes and think hard. You're right if you said it's y equals 2. My horizontal asymptotes are horizontal lines, so they always look like y equals something. So that is my horizontal asymptote. I'll note, if you took the limit as x went to minus infinity, what would happen? Well, you'd throw away the terms that were lower order. You'd only look at 2x over x. Then you'd have the limit as x goes to minus infinity of 2, and so you'd also get 2. Okay. And so you'll see what happens with these rational functions is actually whenever they have a horizontal asymptote, it's the same in both directions. That means it's the same towards positive infinity and towards negative infinity, just like in this example I drew you, where there is a horizontal asymptote at 3 in the positive infinity direction and the negative infinity direction. Okay, what about this one? Well, in order to find the horizontal asymptote, I need to take the limit as x goes to infinity of x minus 1 over x squared minus 4. I'm going to throw away the stuff that's not the highest order. And now I have to think back to what's the limit as x goes to infinity of 1 over x? But that is 0. Okay. So the horizontal asymptote of this function is y equals 0. What about the vertical asymptotes? Well, the vertical asymptotes come from places where the denominator is 0. In this case, x plus 2, that's 0 when x is minus 2. And so my vertical asymptote here is x equals minus 2. And because it's a vertical line, I write it just like that, x equals minus 2. That's the equation of my vertical asymptote. That's my only vertical asymptote. In the case of g of x, the denominator is 0 when x squared minus 4 is 0. That actually happens both at x equals plus 2 and at x equals minus 2. Now, I'll notice, technically, in order to have an x-intercept, I need to have the numerator be 0 and not the denominator. And in order to have a vertical asymptote, I need the denominator to be 0 and not the numerator. If both of them happen to be 0, then I'd actually end up with a hole. That was what this whole business was about. Okay. However, since I was calculating both of them anyway, I didn't bother checking the other piece because I'll know if I get to the end of this and I find out that I have an x-intercept at 2, 0, and I also have a vertical asymptote at x equals 2, that tells me that actually the numerator and denominator were both 0, and I need to go back and reconsider. So you can check it at the time, or you can just wait and check for overlaps at the end, because when you try and draw a picture of something that has both an x-intercept and a vertical asymptote at the same place, it's going to occur to you that something is wrong. Okay, so now I want to draw graphs of these things. So let's start by drawing a graph here of f of x. Okay, so I will try and draw my axes as relatively clean as possible. Let's see, I've got a y-intercept at minus 2. So that's on the graph. I've got an x-intercept at 2. So that's on the graph. I've got a horizontal asymptote of y equals 2. And I've got a vertical asymptote of x equals minus 2, which is that. Okay, so what do I know? From what I've written down and described so far, I know my graph has these two asymptotes, and that it passes through these 2 points. The only thing I think I don't know is what happens at this vertical asymptote. Namely, does the tail end up going off this side or this side? And same on this side. Now, the fact that these 2 points are on the graph is probably enough to convince me that it's not going to somehow go through these points and then shoot up here. And you'd be right, so I'll go ahead and do this way. Okay, so something like that. What happens up here, though, I can figure that out by calculating the limit as x goes to minus 2 from the left of 2x minus 4 divided by x plus 2. Okay. And remember, this is going to tell me, does the other piece of the graph show up over here or show up here? Okay. And so what do? Well, I go back to my usual technique for calculating these things, which is to say, hey, at minus 2, this thing is near minus 8. At minus 2, this thing is near 0. But it's 0 from the left, so that means my number is a little less than negative 2. And so if I take a number that's a little less than negative 2 and add 2 to it, it's still negative. Okay, and so this is a negative 8 divided by a negative 0. And so that means this is a plus infinity, which means that this direction runs off this part of the page. So I've got something that looks like that. And so the graph that I have of this function looks something like the red piece and the black piece put together. Okay. And so that's to emphasize how all of the limit stuff connects to the graph and connects to these notions of a horizontal asymptote and a vertical asymptote. Let's do the same thing for our friend g of x. So our friend g of x has a y-intercept that's just at a quarter, so I'm going to put that a very tiny nudge up there. It has an x-intercept at 1. It has a horizontal asymptote at y equals 0. So that means the horizontal asymptote is actually the x-axis, because the x-axis is the line y equals 0. And then it has two vertical asymptotes, one at plus 2 and one at minus 2. So there's the one at plus 2. Here's the one at minus 2. Okay, and I've got to figure out how all of the pieces fit together. It's got to pass through that line and end up near this, and all of those sorts of pieces. So let's deal with the plus 2 one first. Namely, let's take a look at what happens if I take the limit as x goes to 2 from the right of x minus 1 over x squared minus 4. Okay, x is a little bigger than 2, so this number's about plus 1. And if x is a little bigger than 2, x squared minus 4, well, if x is a little bigger than 2, x squared is a little bigger than 4, so that minus 4 is still going to be positive. So that will go ahead and pull up my little plus 0. And so that means as I approach 2 from the right, this thing is going to plus infinity. Now, before I draw it, picture where that's going to put something in my graph. Have you pictured it? Good. So this is 2. So 2 from the right, that means this side, is going to plus infinity, the output. So that means I'm getting a nice asymptote that looks like this. And I know that I have to have a horizontal asymptote here at 0, so this line has to approach that. So I've got that piece taken care of. What if I approached 2 from the left? Okay, that's going to tell me what happens on this side, the left side of this asymptote. Okay, well. Okay, the numerator is still going to be plus 1. But the denominator, now I'm taking a number a little less than 2 and squaring it. And if I square a number that's a little less than 2, I'm going to get a number that's a little less than 4. So when I then subtract 4, I'm going to have something negative. And so I'm going to here get a negative 0, which means that this limit, in fact, is minus infinity. which means that I'm going to have something that passes through those 2 points and ends up running down there in the direction of the negative infinity output. I'll tell you what happens for the other 2, but I'll let you check for yourself. So if you want, pause the video and go calculate what happens on this line. But if you do the same thing, I'll tell you what happens. Spoilers coming. 3, 2, 1. Okay. What happens is that it ends up going up like this. Okay, so the limit as x goes to -2 from the right is plus infinity. And then the other piece ends up looking like this. Okay, so meeting this horizontal asymptote and this vertical asymptote. And so the limit as x goes to -2 from the left ends up being minus infinity. And so the graph ends up looking like this. Okay, so I know that was a lot of sections, but it all ties together around this idea of a limit and what these things look like in graphs. And so, just as a reminder, here is our test 3 information. Test 3 is going to be on Friday, October 23rd, and it's going to cover this list of sections. And as a reminder, what are each of these things? This was the section on identifying graphs and their properties. This was the section on piecewise functions. You'll notice both of these were here because they tie to the rest of stuff with limits. This was the section on the average rate of change and instantaneous rate of change, which were both connected to why we started talking about limits in the first place. This was our section on limits. This is the longest and the most important section out of everything we have done, so make sure you review this section. This was the section on limits at infinity, which just connected to horizontal asymptotes in the discussion we just had. This was our discussion on one-sided limits, which connected to vertical asymptotes in the discussion we just had. And finally, this section is putting all the pieces together to talk about the idea of vertical and horizontal asymptotes in general. So it's a good chunk of material to review, but you've got plenty of time. But that's all for now. I'll see you next week.